Okay, Michael, so what I have here on the screen is two formulas that tell you how to compute the probability that a particular action A is the optimal one, given some evidence, which I'm calling D sub A. That is, D is the data, the set of labels, the number of the times you've said yes or no for A being the optimal action, in both the general case, where there can be any number of policies that are optimal, that is, any number of actions in a particular state that could be optimal, versus the case where there can be only one, the Highlander case. Okay, so I'm just going to kind of read this out to you, and you can just ask me any questions you want, but we'll sort of see where it goes. So we should read the first equation in the following way. So all of these are for a particular state, and you just can apply this in every given state because we're living in Markov decision process land, and we don't have to worry about all the other states. We can just worry about the state we happen to be in. This is the probability for a given state. Action A is the optimal one given a sequence of labels that say, yes, this is optimal, no, this is not optimal, is equal to this quantity. C is just the probability the human is correct, which was 0.8 in our last quiz and was 1 in the quiz before then, raised to the power delta sub A. Now, what is delta sub A? Well, delta is just the difference between the number of times you said yes and the number of times you said no to action A. Now, what does that really mean? Well, remember, as you said when you were kind of thinking this out loud for the first one, that what we really got is multinomials and binomials. No, I mean, binomial is a special case of a multinomial. So what we really have is multinomials. So what we're really doing is flipping coins. So every time you sort of flip a coin, you're getting some evidence of whether the coin comes up heads or tails more often. And so what you have here is delta basically is a sufficient statistic that summarizes the entire sequence that you get. Now, what this means in practice is that every time I say yes and no, it's as if they cancel each other out. They drive me back towards the uniform distribution, or whatever your prior happens to be. Now, a lot of people find that difficult to wrap their heads around. It feels like if I flip a coin twice and it comes up heads once and tails once, that's evidence that it's a half. But if I flip a coin 1,000 times and 500 times it says yes and 500 times it says no, that's somehow more evidence that it's a half. And that's true, but actually in both cases, the maximum likelihood answer is still 1/2. It's just in the second case, you're even more confident about it. And what we're doing here is we're measuring basically the mean, not the variance. Does that make sense?
Yeah, I think so. Right. So it's in some sense, it's not telling us how sure we are of the answer. It's really just saying what the answer is, the best guess as to the answer.
Exactly right. And what this delta kind of summarizes for you is the only thing that matters is how many times you said yes versus how many times you said no, not how many times you said yes on its own. So in the general case, what we're really saying here is something kind of neat, which is that we can treat every single action as if they're independent. And so the probability that A is optimal depends only upon what you've told me about A. It doesn't depend upon anything else, because as we did in the first example, if you tell me that the first action is optimal, but all of them could be optimal, there's multiple optimal policies, then the fact you told me something about that action doesn't actually tell me anything about any of the other actions. And so what we have here is basically the probability that I would see that many times you've said yes, normalized by the probability I would see that many times that you would say yes, versus I would have said all those times and been wrong about it. So C to the delta A is sort of under the assumption that you are correct, and 1 minus C is under the assumption you are not correct. And that just falls out of the binomial distribution. And if we plug in our original answers, you would see that you end up with the same thing that we got before in the special case where you've only seen one label. You with me?
Yeah, that's cool. Yeah, I think so. So because it's the binomial case, 1 per action, we're not looking at any of the other actions. So the denominator there comes from essentially the count of how likely it is that we'd have that delta number, versus that if we were wrong, we would have that delta number, the 1 minus C. So yeah, I think that feels right to me.